Hello and welcome to the channel. Here is one of the problems offered at Olimpiada Matemática Española, the Spanish math contest in year 2020. The link to the page will be given under the video. When I first looked at the page, I didn't notice the link to the solution, so I solved it myself and even prepared the video. Only when it was almost ready for the submission, I took another look at the page, and you can imagine my frustration. The solution was practically identical to mine, with few very minor differences you may notice. However, the description is so sketchy that someone could hardly understand it, while the main statement is practically left unproven. So after all, I will publish that video because I believe it will be useful, and well, I don't like my effort to be wasted. And I'm going to place the link to the solution as well, so you will not repeat my mistake. The contest presumably took place in the coastal city of Almeria, Andalusia. However, if I understand the word telemático correctly, that was actually an online contest, so the reference to Almeria could be really symbolic. Anyway, here are the nice pictures from this wonderful city for someone who, like me, cannot travel to Europe at the moment. And the problem, of course. Consider a sequence of whole numbers f of n defined by the following conditions. F of 1 is 1. If n is even, then f of n equals f of half n. If n is odd and f of n minus 1 is odd, then f of n is f of n minus 1 minus 1. If n is still odd, but f of n minus 1 is even, then f of n equals f of n minus 1 plus 1. Two questions are asked. Question A. Find the value of f of 2 to the power of 2020 minus 1. Question B. Prove that the sequence isn't periodic. In other words, there are no positive integers t and n is 0, such as f of n plus t equals f of n for any n starting with n0. Rather unusual conditions, but that's what we have to deal with. Let's start, with your kind permission, I will slightly modify the conditions. Instead of f of 1 equals 1, I place f of 0 equals 0. Since f of 1 is no longer given, it has to be computed. Argument 1 is an odd number. The preceding value f of 0 is 0, which is an even number. So we use rule number 4, from which we conclude that f of 1 equals f of 0 plus 1, which is 1. Just what we had in the original condition. So nothing crucial really happened after the modification, only instead of counting from 1, we now count from 0, which is more convenient for me as a computer programmer. In addition, you will see that this really has some advantages. Let's evaluate a few more values to get a feeling of the sequence. F of 2. The argument is an even number, so we use rule number 2, which is straightforward. F of 2 equals f of 1 equals 1. Argument 3 is again an odd number, and again we refer to the preceding value. F of 2 is 1, and this is an odd number, so we use rule number 3, according to which f of 3 equals f of 2 minus 1, which is 0. F of 4 is just f of 2, which is 1. Now to f of 5. The preceding value f of 4 is 1, which is an odd number, so we use rule number 3. F of 6 equals f3, which is 0. F of 7 equals f6 plus 1, according to rule number 4. Normally, I would look for a repeating pattern, but the conditions claim that the sequence is non-periodic, so there should be no repeating pattern, and I trust the conditions. Nevertheless, one pattern can be easily observed. If the argument is a power of 2, this power can be gradually reduced until we get f of 1, which is 1. This means that f of any power of 2 is 1. But question A is actually about 2 to the power of 2020 minus 1, which is the preceding argument. So let's consider a subsequence of numbers Cn equals 2 to the power of n minus 1, and try to find the pattern for this subsequence. Here are the 4 starting values, and you certainly can see the pattern. You only need to prove it. So let's prove statement number 1. F of 2 to the power of n minus 1 equals 0 if n is an even number and 1 if n is an odd number. Again, C of n equals 2 to the power of n minus 1, and we need to prove that f of c with an even index is 0, but f of c with an odd index is 1. Quite obviously, we are going to prove that by induction, for which we need a recursive formula for Cn. So we write Cn plus 1 equals 2 to the power of n plus 1 minus 1. And then we represent 2 to the power of n plus 1 as 2 times 2 to the power of n, and minus 1 as minus 2 plus 1. So 2 is a common factor, and the value in brackets is just Cn. So we get 2 times Cn plus 1. We use the induction by k. The base case corresponds to k equals 0. F of c with index to k is f of 0, which is 0. F of c with index to k plus 1 is f of 1, which is 1. Both values agree with statement 1, and we move to the induction step. We assume that statement 1 holds for k equal q. So f of c with index to q equals 0, and f of c with index to q plus 1 equals 1. We are going to prove statement 1 for k equals q plus 1, which means that f of c with index to q plus 2 equals 0, and f of c with index to q plus 3 equals 1. And we are out of space, so I need to wipe some lines which are no longer needed. So according to the recursive formula, we have f of c with index to q plus 2 equals f of 2c with index to q plus 1 plus 1. For an odd argument, we need to find the preceding value, for which we can just drop factor 2, and according to the assumption, f of c with index to q plus 1 equals 1. This is an odd value, so we use rule number 3, and we get f of c with index to q plus 2 equals 0. For index to q plus 3, we again use the recursive formula, and again we drop factor 2, and for index to q plus 2, the value is already known. This is 0, which is even, so this time we use rule number 4, and we find that f of c with index to q plus 3 equals 1. The values for indices 2q plus 2 and 2q plus 3 match the expectation. The induction step is concluded, and statement 1 is proven. In particular, since number 2020 is even, we know that f to the power of 2020 minus 1 is 0. This answers question A, but there is still question B about the periodicity of the sequence, and all my attempts to prove that failed. Eventually I had to admit the false start and look for a completely different approach. This time we are going to use a binary system, which is a system-based tool. For someone who is not a computer programmer and doesn't feel very confident with it, here are some facts. Binary system uses only 2 digits, 0 and 1. So number 0 is still 0 as binary, and number 1 is still 1. However, digit 2 does not exist in binary system, so for number 2 we need 2 digits, 1 and 0. Number 3 is 1, 1, and once we come to number 4, we realize that all 2-digit binary numbers are used. Therefore, for number 4, we need 3 binary digits, 1, 0, and 0. 3 digits are sufficient for 5, 6, and 7, but number 7 has all binary digits equal to 1. Therefore, this is the maximum 3-digit binary number. So number 8 is represented as a 4-digit number, which is 1,000,000. It can be assumed that any positive binary integer starts with 1, as leading zeros can be discarded. It can be observed that any power of 2, which is 2 to the power of k, is represented by 1 followed by k zeros. This is the smallest binary number having k plus 1 digits. The preceding number, 2 to the power of k minus 1, for a positive k, is a k-digit number having all ones. This is the biggest k-digit binary number. The decimal analog of z is 10 to the power of k minus 1 equals k nines. Decimal system has base 10 and 9 as the biggest digit, while the binary system has base 2 and 1 is the biggest digit. So similarity is quite obvious. Multiplication by a power of 2 in binary system means multiplication by 1 with k zeros. And similarly to the decimal system, it results in appending k zeros to the original number. For example, 5 times 8 in decimal system is 101 times 1,000,000 in the binary system, so we append 3 zeros to the original number and get a 6-digit number. The following table lists first 10 values of f. For each number it shows the binary equivalent and corresponding value of f. Try to figure out the pattern and think of the way to prove it. So let's use d of n for the total number of digits in the binary representation of n, while O of n will be the number of ones in this representation. 2 to the power of k is a k plus 1 digit number with a single 1. Therefore, d of 2 to the power of k is k plus 1, while the value of O is just 1. By the way, any other positive number has the value of O more than 1. Now consider the preceding number, 2 to the power of k minus 1. When k is positive, it is represented by k ones, in which case the values of d and O are both equal to k. For other numbers, the value of O will be strictly less than the value of d. If k is 0, then 2 to the power of k minus 1 is also 0. In this case, the value of O is 0, which matches the general formula, and the value of d is 1. We are going to prove statement number 2. The value of f of n is 0 when the number of ones is even, and 1 when the number of ones is odd. In other words, the value of f can be either 0 or 1, and it always has the same parity as the number of ones. It can be written as a single expression, f of n equals O of n modulo 2, but we wouldn't use it, as someone might be unfamiliar with this notation. And of course this statement is much more general than statement number 1, since it covers not only a power of 2, but any whole number. And again we use induction. This time we do it by the number of digits. Base case when d of n is 1. There are two one-digit numbers, 0 and 1, and their values nicely fit the statement. For the induction step, we assume that the statement holds for any k-digit binary number, and we are going to prove it for a k plus 1 digit binary number. And again I clear some lines. So, let a be a k plus 1 digit number with digits a0, a1, etc. up to ak. Of course you realize that the sequence of a's with indices is not a multiplication, but just digits of a number, so I will not use any special marks. Let's split out the last bit, a0. I replaced it by 0 and added as a separate number. Appending a 0 is the same as multiplication by 2. So we can write that as 2 times the number formed by the leading k digits plus a0. Using letter b for the number formed by the leading k digits, we can write a equals 2b plus a0. Note that b is a k-digit number. Therefore, according to the assumption, statement 2 applies to number b. Depending on the value of a0, there are two cases. Case 1. a0 is 0, so a and b have same number of ones. A is an even number, therefore according to rule 2, f of a equals f of b. Same number of ones and same value of f, therefore statement 2 works for case 1. Case 2, a0 equals 1. This time number a has another 1, which means that O of a and O of b have different parity. So the values of f are expected to be different for a and b. Let's see if this is really so. Now a is an odd number, so the value of f of a depends on the previous value, which is f of b. Applying statement 2 to b gives f of b equals 0 if O of b is an even number, and 1 if O of b is an odd number. This splits case 2 into two subcases. Subcase 2.1. O of a is an even number. Hence, O of b must be odd. And f of a minus 1, which is f of b, equals 1. This is an odd number, so according to rule 3, f of a is 0, which is an expected value for the even number of ones. If O of a is odd, then O of b is even. And f of a minus 1 is 0. 0 is an even number, so we apply rule number 4 and get f of a equals 1. Again, we obtain the expected value for f. The induction step is complete. and the statement 2 is proven. In particular, for C of n, which is 2 to the power of n minus 1, O of Cn equals n, and after substituting that into the formula for statement 2, we get exactly the formula for statement 1. And again, we answer question A, but this time we step adelante to question B. Statement number 3. Sequence f of n is non-periodic, which of course is proven by a contradiction. So let's assume that there is a positive integer p named period and a starting index s, so that for any n greater or equal than s, adding the period to n doesn't change the value of f. Quite obviously, any multiple of p is also a period, since the periodic rule can be applied several times until we eventually get to f of n. Let dp be the number of binary digits in the period, and ds the number of binary digits in the starting index. We can always assume that p has more binary digits than s, because otherwise we can append sufficient number of zeros to the period and get value p prime with more digits than s. Since appending zeros is effectively multiplication by a power of 2, p prime as a multiple of p is another period of f, so we can just use p prime instead of p. A period may have either even or odd number of ones. Consider each case separately. Case 1. O of p is an odd number. Take n equals 2 to the power of dp. We know that f of a power of 2 is 1. Number n has dp plus 1 digits, and dp is more than ds. Therefore, n has more digits than s, so n is greater than s. This means that the periodic rule is applicable to n, so f of n plus p equals f of n and equals 1. Let's find out if this is really the case. The binary representation of n is 1 followed by dp zeros. P is a dp digit number, and it is positive, so it starts with 1. Adding up these two numbers puts an extra 1 in front of p. Therefore, O of n plus p equals O of p plus 1. But O of p is an odd number. Therefore, O of n plus p is even. According to statement 2, it means that f of n plus p is 0, which is a contradiction. This finalizes case 1, and we move on to case 2, when O of p is even. This time we take 2 to the power of dp minus 1 for n. And again, f of n is 1. Now n has dp digits, but it still has more digits than s. And again, the periodic rule is applicable to n, so f of n plus p equals f of n equals 1. Let's see what we have this time. Now, adding the numbers results in adding ones. So starting 1 in the period is replaced by 0. Therefore, an extra 1 doesn't change the total number of ones in p. O of n plus p equals O of p. Now O of p is an even number, so is O of n plus p. And again we have f of n plus p is 0, And again, this is a contradiction, but this time the proof of statement 3 is complete. Me siento agotado completamente. I wonder if the binary system is actually taught at typical Spanish school. After all, the first approach might be the right way to tackle the problem, but I just couldn't make it to the full stop. Anyway, I am quite happy with my solution, and that's it.